Hi, I'm Atul and I am based in East London right now.
Hi, I'm Paul and I'm an A-level chemistry tutor based in Burnley, Lancashire right now. So today we're going to have a look at the electrophilic addition of asymmetrical alkenes. That's basically just alkenes that aren't symmetrical like ethene. And the reaction I'm going to have a look at is methylpropene and hydrogen bromide. So the first thing we need to do is draw our methylpropene. It's an alkene, so it's got a carbon-carbon double bond. And we have 3 carbons in a row because it's propene, and we have a methyl group attached as well. So methyl propene, then just make sure all our carbons have 4 bonds. 2, 3, 4. So that's methyl bromine. Now draw our hydrogen bromide. And we can show that this is a polar bond because the bromine is more negative, electronegative than the hydrogen. So that attracts electrons towards it. And the hydrogen is delta positive because electrons have been withdrawn away from it. And the hydrogen, the delta plus hydrogen, is our electrophile, which is an electron pair acceptor. And it will accept electrons from the double bond, a pair of electrons from the double bond. And therefore, the hydrogen bromide bond electrons can go to the bromine. And therefore, that gives us and now we have a choice of which carbon the hydrogen adds onto. And so what we can do, we can show what happens if we add on to each carbon in turn. So first we'll add on to the first carbon. And the other carbon has lost electrons, so that gets a positive charge. Show that up here. And everything else stays the same. And then we can have the Br minus, which took electrons from the hydrogen bromine bond, and that can form a bond with the carbon. And our other option is the hydrogen could attach to the second carbon, and the first carbon gets the positive charge. And then the bromine could form a bond with the first carbon. Okay, so I'll just move all this to the side so we can see what happens next. So here we would attach the bromine and here we would end up with bromine So, and in fact, we get both these products in the reaction, but one is the major product and one is the minor product. And to decide which is the major and the minor, we look at the carbocations that were formed here. So the first carbocation is a tertiary carbocation because the carbon with the charge on it is attached to 3 alkyl groups. And that alkyl groups are electron pushing, so they reduce the positive charge on the carbon and therefore make this more stable. So tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. So our second carbocation here, we look at the carbon with the positive charge, that just has 1 alkyl group attached to it. And therefore this one is a tertiary carbocation, this one is a primary carbocation, and therefore the first product, our 2-bromo, is our major product because it's coming from the more stable carbocation, and our second one is our minor product because it's coming from our primary carbocation, which is less stable than our tertiary carbocation.
Right. So that's yeah, just to like double check a few things. Cation, positive charge. So obviously carbocation is a sort of temporary state where it's a hydrocarbon cation.
Yeah, it's an intermediate in our reaction, yeah.
And the degree of carbocationness, to so to speak, primary, secondary, and tertiary, is the number of groups attached to it, like full CH3, C2H5, etc. groups, like
yeah,
alkyl
full
groups.
alkyl groups. You can get away with just looking at the number of carbons that's attached to the carbon with the charge on it.
And because this is more stable, for all the reasons you specified, there's just more of this existing in the first place in this kind of situation. So that because if more exists, then more of it will react with these bromide ions.
Yeah, it's called the inductive effect of the alkyl groups, but essentially they're electron pushing rather than electron withdrawing groups.
Right.
So the more of the electron pushing groups there are, then the reduced positiveness of the carbocation, and therefore it's more stable.
Great. Sounds good. Yeah, just got it. I just mentally checking up on a few things. Yeah, that sounds good. Great. Look forward to next in this kind of organic chemistry series of videos. Yeah.
Okay. Thanks, Atul.
Great. Bye for now.
Bye.
Bye.